This is lecture 8A for Calculus 2 on the surface area of a figure of revolution. Now we're going to look at the surface area of a figure of a solid of revolution. All right. So what we have, if you can remember from the, let me get a pen here, from a figure of revolution, okay, and say in some coordinate system x, y, let's just do with respect to x. If I have some shape here, this will be my function with respect to x, and I rotate this about this axis, and that creates the solid of revolution. And what I want is the surface area over the solid. All right. So to do this problem, I do the usual slicing up, and I slice the problem into bands. So this is a band. Here's another band. It's like a big circular band. And I calculate the surface area of each of these bands and then add them up. There are two choices for these approximations. One would be cylindrical bands. We're saying this is just a little cylinder here and here. The other is conical, saying that it's really a little cone. It's an interesting result because you think the cylinder would give us fine results. It looks similar to something we've done in the past to calculate volumes. And the conical, well, that might be a little hard to calculate. It turns out that when you use the cylindrical approximation, it does not give the correct results. But the conical section does, and the conical bands will require using the arc length. For the cylindrical approximation, the one that doesn't work, but I'll just show it to you for completeness, is that you assume you have each band, change to a pin here, each band is just a little tiny cylinder. Okay, it's a figure of revolution, so here's the x-axis coming right through it. I'll draw it like that. So now what is the surface area of each band? All right. The surface area of the cylinder is 2 pi times this length y. If this is the nth band, that's why the y to the n. That is, okay, 2 pi yn is the circumference all the way around the band, and delta x is the length, height, whatever, length, I guess you call that, of the band. So for a cylinder, it would be 2 pi r times the height. For the surface area, here you've got 2 pi, and y is this distance up to here. For example, if you had another cylindrical band up here, this is y, say n plus 1, and then there's your delta x here. Okay, 2 pi y dx. Take the limit, and you get a definite integral from, should have put some values out of, from say a to b, and this might be a figure of revolution here, and this is a, this is b, and it looks like that. Okay, now seems simple enough, but when you apply it to figures of revolution that have known surface areas, you do not get the exact results, but you do get the same answer when you use a conical approximation. I'll show you that in the next slide. Now for a conical approximation, that is approximating each one of these, okay, here's a little band, but instead of approximating it as a cylinder, approximate it as a little piece of a cone. All right, so we have 2 pi times the average radius. Okay, for the nth band, the average radius would be yn, and here would be yn plus 1, the average. So the average radius is given right here. All right. Okay, if the band is infinitesimally small, this is going to shrink. So instead of having these different y values, which is just values of the function at these two endpoints, we would just, it becomes f of x in the limit. Okay, now you need the length along here. Before it was delta x, but because we're approximating this as a cone, we need this length here. This length turns out to be the slant height. The slant height is just the arc length, and we have an expression for that right here. That's how we assemble. This is a surface area for a figure of revolution. We put in all these pieces together. S is the surface area for the figure of revolution generated by some function f of x. All right. The first term is a 2 pi r, which is 2 pi times f of x in the limit, and now we have the arc length, 1 plus the derivative squared, square root of that, and integrating over dx. We could do the same thing with respect to y.